In this video, we're going to look at the third question from the tutorial on structures from the Mechanisms and Structures unit. And in these questions, we're asked to draw a free body diagram and to calculate the values of the reaction forces indicated in the diagram, RA and RB. So we will begin here by doing exactly that. First, we'll draw the free body diagram. And when we're drawing a free body diagram, we're drawing the simplest possible version of what's happening in our question that preserves the values and position of all forces and any length in the diagram as well. So it means that we can reduce this lighting gantry just to a single line, which represents the point where all forces are applied. So I'll draw a line in here on our page. Now we have supports at either end of the gantry. So I'm going to draw vertical forces in here for RA and RB. I'm just copying these from the position on the diagram. And there's two loads suspended, two pieces of equipment, lighting suspended from this gantry. And I mark them in here as well. This is not a scale diagram, so it can be drawn in approximately. We will mark in all the values as indicated in the question. We've got a 45 kilonewton force here, and we have, this is exactly halfway along here, we have a 25 kilonewton force here. And I'm marking all of the distances we're given in the question as well. So we're told that this 45 kilonewton force is 1.2 meters on the left-hand side. The 25 kilonewton force is 2.5 meters from the right-hand side. And the length of the entire gantry that we're considering, and this will help us in the question, is 5 meters. So that's the free body diagram. That's all we have to do. So it looks quite similar to the original diagram, just with all the kind of details of the exact shapes removed. All of the forces, including the reaction forces we haven't yet calculated, and all length are translated onto the free body diagram. Now we want to find out RA and RB. Now we could start by thinking about vertical forces, and we find that RA plus RB would have to be equal to the two downward forces added together. But that wouldn't help us find out the individual values, and that's because we still wouldn't have enough information. We'd know what they added up to together, but we wouldn't know what individually they were. Now, in this type of question, what we have to use is moment, as well as having a total vertical force of 0, so upwards and downward forces being balanced. At every point in the lighting gantry, all of the moments, either the clockwise and anti-clockwise turning effects, are balanced as well. And in order to use moment to find out one of our values, RA or RB, we choose to find the moment about one point at the end of the beam. And we choose this point because whatever point we choose, we want to not include one of these two forces. Because since we're calculating moments, if we're at the point, we don't include that force because it's 0 distance away from itself. We could pick either point, but for no particular reason, we'll go for A as well. So we're considering this point here. Mark it in red just now so you can see what I'm talking about as I do it. And we know that the total of all the moments at point A has to be 0. That is to say that all of the clockwise moments are equal to the sum of the anti-clockwise moments. So looking at point A here, which forces would turn the beam clockwise and which would turn it anti-clockwise? Well, if we are positioned at this red dot here and we're looking out to the right, that's where the gantry is extending to. Anything pulling the gantry down is a clockwise moment. If this was able to move freely in a circle, pulling that gantry down to the right would move it clockwise. So that means that our two labelled forces of 45 and 25 kilonewtons are our two clockwise moments. And there's only one other force acting up the way, And because it's acting up the way and to the right, that's our anti-clockwise moment. So we get an anti-clockwise moment due to the force RB, which we don't know. So I should make a wee note to say at point A, because it is important, and just to make it clear, point A and point B, the two sides of the beam, it is important that we take the moment at a particular point. The calculation will change if we took it at a different part of the beam. So let's look at clockwise moments. Well, we have a force of 45 kilonewtons, and with the moment we multiply the force by the distance that force is applied from the point we're considering. So we can see from the diagram the 45 kilonewton force is applied 1.2 meters away from A. So we multiply this by 1.2. Then we're going to have a clockwise moment due to 25 kilonewton force. And while we're not specifically given the distance from A to the 25, well, we can work out that if the whole beam is 5 meters long and it's 2.5 from the 25 to the other side, 5 minus 2.5 is equal to 2.5 meters. The 25 kilonewton force, as it turns out, is exactly halfway along the gantry. So it's going to be 2.5 kilonewtons multiplied by 2.5 meters. And that takes care of all of the clockwise moments. Now, to consider the anti-clockwise moment, as I said, the reaction force at B is acting up and to the right. So if we imagine this gantry sticking out the way, if it was free to rotate at point A and the force at B was the only force, it would be pulling it in an anti-clockwise rotation. This is our anti-clockwise moment. And the size of the force is an unknown value, which we're calling RB. And it's multiplied by the distance this force is from A, indicated by a red dot. And of course, the distance is the length of the whole gantry. So it's going to be 5 meters. So we can now do these calculations to work out what RB is. So we have 45 times 1.2, which is 54. And we've got 25 times 2.5, which I think is 62. I'll just double check that. 62.5, that's right. 62.5. And on the other side of our formula, we just have 5 times RB. So we can add those two numbers on the left-hand side together and swap around our formula. 5 times RB is equal to 116.5. So RB must be equal to 116.5 divided by 5. And that is 23.3 kilonewtons. So we now know the value of the force RB. So we're going to use another piece of information that we have about a static system, and that is that the sum of all the forces act up the way must be equal to the sum. That's what the sigma sign means. I should have reintroduced that. The sum of all the forces acting down the way. So our upward forces from our diagram are RA and RB, and our downward forces are 45 and 25, which means that RA plus RB is equal to 70 kilonewtons. And because we've just worked out what RB is, we can say that RA plus 23.3 is equal to 70. And so subtracting that, we find that RA must be equal to 46.7 kilonewtons. And this is the method you use to solve any problem like this, where we have what's effectively a simply supported structure with two unknown reaction forces. We choose to work out the moments at the point where one of the reaction forces is applied. In this case, we've chosen point A. And doing this calculation will give us the value of the reaction force at the other point. And then we can use information we know about all upwards and downwards forces being equal, the sums of them that is, to give us the other reaction force as we've worked out here. And that concludes everything you need to do to solve question 3.